Hello students, welcome back. Let us resume our discussion in section 3. We completed proof by manipulation. Now let's go to the next, proof by implication. That's the second one right here. Here's an example. Prove this quadratic equation has roots -4/3 and 5/6. This is what we do in 1000 level course. Here's a given equation, factor it, and set the first factor equal to 0 and second factor equal to 0, and consequently we get these two roots. Alright, that's perfect for 1000 level math courses, but in 3000 level we gotta do better. What's the relation between the first line and second line, and the third line, and the fourth line? How are they related, logically? We can write like this. First line, that's a given equation, and that implies the second, and that implies the third, and also here in the third line, we have or operator, or conjunction, and that implies the fourth line, and the conclusion follows in the end. So the flow of logic follow the implication, and then they're all aligned like this, and then please note that there's nothing here, kept empty. So this is a flow of, well, single flow basically. Alright, that's one example, and that example was very similar to the grammatical rules for proof by algebraic manipulation, you see. And instead of equalities aligned and having nothing here, we have logical implication here. Here's another example. This time, let's rewrite this a little bit differently. Pythagorean identity, and by the way, what is sine and what is cosine and things like those? Do you all remember those? So x comma y is this point, and that point is randomized, so I can run this program over and over again, and no matter how many times I run, we have to have a right triangle. So x squared plus y squared is equal to r squared, and that's the starting point. So from there, divide each by r squared. And then manipulate further. R squared over r squared is 1, and then by exponential we have x over r squared and y over r squared respectively. And remember, x over r is cosine and y over r is sine, and that gives us the desired Pythagorean identity. So if you look at these individual lines, then they're all separate. They're independent equalities. How are they related? Like these, as highlighted in blue. This is another example of proof by implication. Here in the previous proof, I used logical implication, double arrow here, because this was simple. But in many cases, we want to be a little bit more specific, how these things are implying one to the other, and the reasoning, and so on and so forth. In that case, we write down all those reasonings like this. And the more complicated the proof, the more complicated these explanations. And because of this reason, proof by logical implication is more versatile than proof by algebraic manipulation. We are going to do this a lot in this course. There are some courses, such as linear algebra, where we do heavily upon proof by algebraic manipulation. But here in number theory, we are going to use proof by logical implication far more. By the way, we can do the same thing by proof by manipulation like this. So we have the equality here, and then further algebraic manipulation, taking a common denominator, and then eventually we are getting 1. Please note that equalities are all aligned and there's nothing here. This is a failed proof, by the way. Yeah, you can write all those, all aligned, but how are they related? This is a checking process. It's not a proof. Close but no cigar. And of course, if you write down all those explanations here, as I did here in proof number 1, then you can make it perfect. But by itself, this is imperfect, incomplete. Here's another example. I'll leave that to you. How about the next example here? Prove that for any x in R, okay, this time we have a universal quantifier. For any real number x, x times 0 is 0. Okay, alright, let's try to prove it through proof by manipulation. Here's an example. 0 is 0 plus 0. I just use additive identity and then use a distributive law to break those off, and then use associativity. No, I didn't use associativity, excuse me. I just subtracted the same thing from both left-hand side and right-hand side. And then I use associativity, and then this subtraction and that subtraction will give us 0. So we have 0 plus 0 like this. And then we can cross out this 0 because 0 doesn't change anything. That's additive identity. Consequently, what did I get? X times 0 is 0. This is a complete proof. And I copied from, I used the term in the textbook, but that textbook was for some other course when we had real analysis in a little bit lower level analysis in place of introduction to proof. We used to use a little bit lower level book. So that's another example of proof by logical implication. Now, how is the first line and second line related, second line and third line related, and so on? Those are right here. So that part here is essential. Without this, okay, all right. This was hard proof, so if you do something like this in Introduction to Proof class, I will give you full credit, but how are all those lines related to each other? That reading should be there to make it perfect. If you use proof by algebraic manipulation, you can do it like this, starting from here and then do some manipulation, and eventually getting to 0. You can do it like this too. And then we have all those reasonings here. Yes, you can do that too. But this is a little bit harder as a matter of fact. How about this one? A times b is 0, then either a is 0 or b is 0. Alright, that's a nice problem. By the way, what is a and what is b? What are those? Are those real numbers? Are those integers? Are those rational numbers? I'd better specify the domain. Okay, let's keep those real numbers. So how do you prove that? If a is not 0, then we divide by a. So if I divide by a, then I'm going to get b equals to 0. If b is not 0, then I divide by b, so a is equal to 0. So divide by a, divide by b. So we have explanations here, the circumstances, and also logical implication. They're mixed up, and they're all working together to present a proof. You see, logical implication, proof by logical implication is more versatile, and not coincidentally, they can be a little bit more complicated and rough. Prove that between any two real numbers there is at least one real number. Okay, this time this one is existential quantifier. We went through a problem on universal quantifier, and this too is actually universal quantifier as a matter of fact. And in this case, yeah, we're dealing with some at least one. They exist, so that's an existential quantifier. So between any two real numbers, okay, that's universal quantifier. And you can write like this. For any pair of real numbers, and they're two different real numbers, not identical. So one must be greater than the other. Without loss of generality, I can assume x is less than y. If not, I can rename switch. Then there exist another real number z such that z is between x and y. Basically, that's what I have to prove. How do you do this? How do you find appropriate z? If you put z as x plus y over 2, the average point, and that's in between x and y. So you can write like this. If you want to write symbolically, then you can kind of write like this. Oops. Okay. Uh-oh, something is not right. It's gotta be internet connection. Let me stop here. I think this may crash. Okay, it didn't crash, but it gave me something. I got nervous. I better not try to write anything new here. Let's just stick to whatever that was written earlier. So that's another example of proof by implication. You can write everything. Okay, finally, how about this? If theta is between 0 and pi over 2, then sine of theta is less than or equal to theta, and theta is less than or equal to tangent of theta. And also, if this is negative, then the opposite inequalities hold. But if I try to write something here, I have a feeling Mathematica may crash again. So I'm not going to do that. Instead, I'll show you. Here's a hint. Look at the picture. Area of the smaller triangle and area of the sector and area of the large triangle. Which is biggest? Large one is bigger, and the middle sector and the smaller triangle. That's going to be the order. So that's going to be the starting point. And then express those areas using appropriate trigonometry. Base times height times 1/2, and 1/2 times radius squared times theta, and base times height times 1/2. If you do all those, this, and eventually you're going to get a relation between sine and theta and tangent. The radius is 1, so distance from O to A is 1, so you don't really have to specify. In the end, what you get is this. You see, things can get pretty complicated. You can use pictures, you can use all kind of things.